So, let's get started. I'm Philipp. I'm from Vienna. I always describe myself or my city like Vienna is the city of fatty foods, classical architecture, and music, or beautiful women, or yeah, everybody knows Conchita. We needed her to win something. So, I work for Elastic, the company behind Elasticsearch and some other products. I'm actually in the infrastructure team, so I'm normally doing stuff like AWS, testing with Jenkins, Ansible Chef Puppet, Docker images, or the rest of the team. But I'm also spending lots of time at conferences like today, so this is actually kind of a Unix pipe. So I kind of piped that out into developer advocacy. So today I'm more on the talking about the good stuff we do. And if you ever want to visit Vienna, I'm running some local meetups, one about databases, one about more on the theoretical side, and we're always happy to have visitors. So, who uses databases? Good, that's a good start. Who uses full-text search? Okay, that's also quite a few. What are you using? Who's using Elasticsearch already? Okay, a few. Okay. So let's see how much new stuff I can show those. Who is using something else? Who is using Solar? Solar? Yeah, okay. Who is using something entirely different? Yes? Plain Lucene. Oh, yeah, okay. Plain Lucene is... but the nice thing is, the stuff I'm talking about today, while I will use the Elasticsearch query API, it's totally applicable to plain Lucene and Solar and Elasticsearch because it's all Lucene. Kind of the stuff we will cover is Lucene anyway. So generally, what is the difference between databases and full-text search? My explanation always looks something like this. Like, this here is the database side, and this is the full-text search side. Databases are very much black and white. You store something, and then you want to retrieve it. It's not about fuzziness or any shades of gray. It's really this, like you have something, and you want to find exactly that value, and you want to retrieve it. So that is the black and white side. But reality has more to offer. Like, there are these shades of gray. In reality, stuff might even be in color. So full-text search is still not really reality. That's why I kept it in shades of gray, but it's kind of seeing more subtle differences. Like, you don't care about an exact match only, but you care just like a concept or a term or something you're looking for. You probably don't even care about is it a noun or an adjective. You just care for the concept you want to find. So that is kind of the point of full-text search. So this is why the shades of gray. And I know somebody will now say, but I can do stuff like this. So I have my table, and I will just do a wildcard search with a percentage sign at the beginning and a percentage sign at the end. And while it's not fuzzy or anything, it's still like, it just finds anything or that part matching anywhere in my database. So that is not that black and white, is it? But this will fail badly. Why? For two reasons. First one is performance. So if you store stuff in a relational database, and you want to have fast queries, you normally want to do add an index, like normally a B tree. So you have a tree-like structure to retrieve data more quickly. And this works pretty much like a phone book. So in a phone book, people are normally ordered by last name and then first name. So if you know what the last name of somebody starts with, the phone book is totally helping you. Then you can just look it up, and it's very fast. But if you only know a part of the last name, which is probably not the beginning, or if you only know the first name, the phone book does not help you at all. Like, you still need to do the full table scan, or full phone book scan in that example. So finding everybody with the name Philipp in the phone book, yeah, does not work like that. You will need to go through every single entry. And that is slow. So the more entries you have, the slower it will be. So it will just grow linearly with the number of data entries you have. Whereas if you were using a proper index, it would stay pretty flat. So normally it's a log 100. So if you add more entries, it will grow very slowly and your performance will not suffer that badly. But if you have the percentage sign at the beginning, this cannot be used. A B-tree structure can only use if you know the beginning of something, much like the phone book. It cannot use if you just have a partial match. That's just not what a phone book does. So as Yoda then would say, as expected works. So this is kind of a feature of relational databases or B-trees. Like, this is nothing unexpected. And the second thing you're kind of missing out is stuff like fuzziness. You cannot have synonyms. You cannot have a quality attribute, which will be scoring. We'll look into that. So if you have multiple matches, in a full-text search, normally you have different qualities of results. Like, some are better matches than others. And a database does not do that. A database is just there like, give me that thing, I expect it to be there. If it's there, give it to me. If it's not there in exactly that form, I don't care, so there is no quality there. So when storing data, you have some more work to do than in a relational database or also a NoSQL database. In a database, normally you just take the stuff, put it somewhere on disk, probably have it in memory loaded as well, and then just answer to that. But for full-text search, you need to do some more work around it. So the first thing you normally do is you remove any formatting. Formatting would be, for example, HTML tags. Because nobody wants to search for HTML tags. It's just like, does not really add meaning to what you're searching for. It's just like layered information. And you just want to throw that out. Then what you normally do is you tokenize. Tokenizing means you have, for example, one sentence, and you find the tokens of that sentence. And the tokens is basically each of the individual words. So you split on any spaces, on any punctuation marks, you just split on those words. And then the full-text search engine will only look at these words individually. So what a full-text search engine also does not do is it does not really understand your sentence. It is not natural language processing or anything like that. So it does not really know what you mean. It just takes words and operates on these words. So the tokens you extract, that is what we're operating on then. So we have extracted all our independent words. And the next thing is you remove stop words. Stop words are these little words that appear in every single text, basically. So they add very little meaning. They would just blow up your index, and your index would just be too large. So you just throw them out. They add no meaning. They're just increasing your index size. This is like a, and, as, if, not. Words that are in every text, basically. You just get rid of them. And then we do stemming. Stemming basically says, take the word and reduce it to its word root or stem. So in English, this is very easy. You normally, for example, with nouns, you have the S as the plural, and you just cut off that S at the end. And then you don't have a distinction between singular and plural anymore. I've been told that this is much more difficult in Russian. But we'll quickly look at that as well. And finally, what is an optional step is you can have synonyms. So if you have probably multiple terms meaning the same thing, your users might just search for any one of them and still expect them to find the concept you're looking for. So you want to have these synonyms and actually say, okay, these words are all the same. If you type in any one of them, I still want you to find whatever I have in there. Synonyms are very dependent on your specific domain or thing you're doing, so there is no global list of synonyms. Synonyms you will always need to provide yourself, so you will need to provide this list yourself. So, since I work for Elastic, we'll do Elasticsearch examples, but again, it's pretty much the same everywhere. So, how does Elasticsearch actually do its stuff? There is Apache Lucene, which is the core library, that is in Elasticsearch, Solr, and other examples, or other implementations. And that is actually doing the hard work we're covering today. So this is taking your data, running through the entire storage pipeline I've shown you, then storing that on disk, and when you query it, that is also Lucene at work then. So all we are covering basically is the Lucene part. What is Elasticsearch then? It is kind of the shell around it, so it provides a REST API, it provides a query DSL, it distributes the data, it replicates the data. So this is what Elasticsearch is then doing around it. But on the inside, it's still Apache Lucene actually storing the data. And because sometimes there is confusion, sometimes people ask like, okay, so what is the database or what is the actual storage? The thing that stores the data is already Lucene. So you don't have any other backend or anything there. It's just Lucene doing that for you. So, we're using this as an example. Who knows the English movie? What is the quote? Yeah, exactly. These are not the droids you're looking for. And yeah, I've just added the emphasis so we have some HTML there to remove that as well. So we will just run that through our pipeline and see what actually happens. So first thing is we just strip out HTML characters. So we have removed the EM. Because if you do not do that, there would be in the text, the tags would be removed and then just the text EM remains. But nobody is searching for EM for the emphasis, so we just stripped it out. Then we use the standard tokenizer that just splits everything up on spaces and punctuation marks. You can see the final dot is gone, and I've added a bit more space around it. So these are just the tokens we have found. Like all our words, these are the tokens we have in our text. Then we lowercase it, because uppercase and lowercase doesn't make a difference. So we just don't care about it. Just lowercase everything, and we're done. We don't need to care about it. Then remove the stop words, like this is what we had, these are not the droids you're looking for. After removing the stop words, this is what remains. Droids you looking. Because all the other words are stop words. So you can see we need to store much less information than we had before, so our index becomes much smaller. And then we actually stem it. So droids you looking becomes droid you look. So we don't care about look, looks, looking, whatever, it's just reduced to look. And droids, the plural is also just stamped down to droid. So we don't care about singular, plural, or any flexion of the verb. It's just stamped down to its root. And to actually run that, in Elasticsearch it is kind of handy. There is this _analyze endpoint. You can just throw some text at it and then say, okay, I want to do actually these steps here. And it will then just show you what the result is. So we can actually do that live, but it's always more fun to show stuff live. So I'm running Elasticsearch 5.0.1, which is the latest version which came out this week. We had a major release like 3 weeks ago, and this is what I'm showing you today. The thing to visualize stuff is called Kibana, that is our visualization tool, and I'm using, it's called Sense here. Oh no, sorry, it's called Console now, it was called Sense previously, it's just to run queries. So this get slash, you could totally do that in curl as well. Oops, I don't need you. So to run the command I've just shown you, in curl would be curl x get localhost 9200 /. And this is giving you exactly the same result we have here. It's just a much nicer syntax to write. You have syntax highlighting, you have auto-completion. So I'm just using console to run all my examples. But you can totally do the same just with curl. You don't need any fancy tools, but it's not as nice to use. So I will stick to fancy tools. So what we want to do is we have the text we've talked about. These are not the droids you're looking for. And we want to run it through our pipeline. So if you run that, this is what is actually extracted and would then be stored. I'm not storing it actually now. I'm just running it through the pipeline to see what do I actually get. So what I get is, you can see we have the 3 tokens we had, droid, you, look. And it actually knows it was the position 4, 5, and 7, and the actual start and offset. Why do we need the position? The position can be useful if you search for a phrase. So for example, if you search for the phrase droid you, which is a weird phrase, I know, but then it's relevant that they are right after each other. So it starts counting at 0, but the term 0, 1, 2, 3, those were stopwords, so they were removed. And now we have the 4th position, the 5th position, and the 7th position. These are the actual words we're storing. And this information will then be kept in the Lucene index to actually retrieve data again. So yeah, this is what we had. This is the list of stop words. Like, it is not long. It is, or at least for me, always surprisingly short. But still, it contains all these very common words that you have everywhere, and you just throw them away. And of course, you can see this is language dependent. Like, in German, in Russian, in Belarusian, whatever, those will be different stop words. And we can do the same thing in Russian. I've told this is pretty much the same sentence. Agreement? Okay, because I don't know. I always have to believe it. So we have these are not the droids you're looking for, and yeah, unfortunately I don't even know how to pronounce it, but yeah, you know. What do you think remains here? Which words will remain if we run them through the same pipeline? All of them. Let's try that out. So here, I'm using the standard pipeline and I'm just telling it this is actually Russian, because if you use a different language, stuff will totally not work. Like if you use the wrong language, you will use the wrong stop words and the wrong rules for stemming, and then you will pretty much keep the original text. So you need to define the right language, otherwise stuff will break. So if we run that, what we get is this. Yeah, I cannot pronounce it, but it probably makes sense for you. So I think droids remains. One thing that might be unexpected is that the not is missing, right? The not. These are not the droids you're looking for, right? The not is not contained in the sentence anymore. So again, just to reiterate that, full-text search does not really understand your sentence. It does not know, do you mean something in a positive or negative sense, or good or bad? It just takes the words and analyzes based on these words. So the no or not is a stop word. This is just thrown out and it doesn't make a difference. Okay, so yeah, we've seen those are the right, this is the result then. That is how we did it. That is the result. And this is actually the list of supported languages in 5.0. You see Russian is supported. Belarusian, I'm not actually sure how different Belarusian is and how good or bad the results will be if you just use Russian. So you see there are quite a lot of languages are supported. The Western European languages are pretty much all there. In Eastern Europe, it's getting a bit spotty. For example, Slovenian and Slovakian, I mean, those are really tiny languages, but they're not in that list. When I'm in your neighboring country, Ukraine, they always ask, like, what about Ukrainian? Because that seems to be so different that you need your own language support. It was added in the current Lucene version, and we'll have it or expose it in the upcoming Elasticsearch version, which will be, I don't know, a few months out or something like that. Yeah, one of my colleagues did pull request, so now we expose it, so Ukrainian is supported. I had a quick look about Belarusian, and I could not even find an issue for that. Like, I don't know, either is it necessary or is it Russian good enough? It's not? Right. I had a quick look. Like for other languages, I know I find the issues, but for Belarusian, I didn't. I found lots of other stuff like job offerings, but around Lucene and Belarusian, but I didn't find any language support. Yeah, I guess somebody needs to open up a feature request or an issue, and then we'll see what happens. Okay. Going back to English, so I can participate as well. Obi-Wan never told you what happened to your father. Any guesses what happens when I run that through the pipeline I've just shown you? What remains? Yeah? Yeah, now we would need the list of stop words again to have an idea what actually happens. But I'll just show you. Obi-Wan never told you what happened to your father. Like, there are not that many stop words by accident in that text, but this is what remains if you run it through the analyze. Any guesses what happens here? No, I am your father. So no is a stop word, that will be removed, and all the rest remains. No, I don't think so. It's not in the stop word. Where was my list of stop words? Yeah, but it is not really a dictionary. Like it does not really, like the stemming is not that fine-grained. It has some rules for the simple stuff, but it is a total trade-off between how many rules do you need to define, how much memory do they take up, and how much time do you need to process it. So there's a trade-off. The stemming is actually normally pretty coarse-grained, but I've been told that in Russian and Ukrainian it is way more work because the different forms of a word can be so different. But in English, we stick pretty much to very simple rules. So for example, yeah, B is in that list, but M is not in that list, and it's M. You would need the dictionary and say, okay, this word is actually has this flexion, but there is not this dictionary to actually tell you that this is going on. And also it would, since this ran through the pipeline, it would then be also, should have been stored like B, but it is not. Like M and B, like if you have these words and you search for one of them and you want to find the other one, that does not work. If you have the special use case where you would need that, you would need to define it as a synonym, but it's not available by default. And then there are more language-specific rules. For example, in English you have this apostrophe S, which is the possessive, is or has, and that will normally be removed. But this is totally language dependent. For example, in French, you will remove stuff from the beginning and the accents. Whereas in German, you have the umlauts and the scharfes S, or whatever it is called in English. And those will be just the dots from the umlauts will just be removed, and the scharfes S is just a double S, which is the way we pronounce it anyway. So this is just kind of flattened out. So for example, the umlauts in German is just like different forms of a word normally have them sometimes, and sometimes they don't. So you can just throw the umlauts out. So that is an easy rule. But again, I was in Sweden recently, and they said there the umlauts, they have them as well, and they make a huge difference. Like these are actually totally different words then. And I've checked in Swedish, you keep the umlauts. So again, this is dependent on the language, and the system should know what is the right rule for that specific language. And we have something that is also only a plugin and not available by default, which is a phonetic filter, which just takes words and then tries to find different ways, if you just pronounce it, how it could have been written. So for example, Joe could be J or Joe, and blocks could be blocks or BLKS or whatever. Not sure how good it is, and not sure how good it is for different languages, but for some use cases when people don't know how to actually spell something, they only heard it, like how it's pronounced, this is something you could as a plugin as well. So now to actually store something and do something a bit more useful, just 3 terms which are relevant for Elasticsearch then. An index, think of an index pretty much like the database in the relational database. So this is just something that contains your data. Then we have a type, which is often compared to a table, but that is not a good comparison. Think of a type just like an enumeration or just different types of data within one index. So you have, I don't know, quotes, and you could have movie quotes and, I don't know, audio quotes or whatever, or from different sources, or book quotes. So you just have different types of things, but they're kind of the same thing, just different enumerations or types there. And then we have a mapping, which is pretty much the schema in the relational world. In Elasticsearch, you do not need to define your schema up front, but then your schema will be guessed from the first document you insert. And it will only rely on the defaults you have. So if you need to have a different language, you need to define that up front. And if you, for example, have a document and insert that, and in a specific field you have a number, then Elasticsearch will just guess, okay, this field should be a number, and it will store it in the background. And if at some later point you want to insert a string for that field, it will of course fail, because strings and numbers don't match that well. And then you cannot simply alter your schema, you will need to re-index your entire index and fix that. So yeah, be aware and be careful what you define in your mappings. For testing, it's fine just to rely on the defaults, but at least for production, define your mappings manually and very explicitly. And another common question is like, what do I do if I have different languages? The obvious choice would be to use the type, because you have just the type is just kind of, that is a good enumeration, like you have German, English, Russian, and you just define it over that. But that doesn't work because you have statistics, like how common are specific words. So this is the worst option and you should not use that. The two options you can use is, first, you use different indexes. So for example, you have quotes, and you have quotes in German and quotes in Russian. Then you would have quote, the index name would be quotes dash Russian, quotes dash German, whatever languages you have. You just have different indexes, like different databases for different sources. Or you use different fields. So you have quotes, and then you have, I don't know, the title and the actual quote or whatever, and then you would have all these fields would have the language added to it, so you have different fields for each language, but within one common index. So those would be working strategies for different languages if you need to support them. Okay, so now we're defining our mapping. So what we're doing here is, the first thing is we're defining my synonym filter, and in it we say I have droid, and that is equal to machine, and we have father, and that is equal to dad. And yeah, the my synonym filter, we will use that on the next slide again. Here we define the entire pipeline we had previously and add at the end like my synonym filter, so we've added the synonyms now as well. And this is stored as my analyzer. And the final part is like, these three slides are all just one code block. I've just split it up so it's kind of readable. And now I say I have a mapping for the type quotes and the field quote. And yeah, it's just text I'm inserting here, and I will analyze it with my analyzer I have defined on the previous slide. So to actually do that, we can then do that live. So we've seen those. So I create my index Star Wars, and I have my type quotes and my field quote. So I will run that. It will create my index. And then I'm just, I can check it out, like, have I done the right thing? And it will tell me, yes, in the index Star Wars, in the type quotes, in the attribute quote, it is text, and you're using my analyzer. Now the question is like, where is my analyzer, or what is my analyzer actually? Yeah, it's a different endpoint. On the index, you just say settings, and that will return, okay. These are, this is the entire pipeline you have. And it will also know, okay, I replicate the data one time, and I normally split it up into 5 different pieces to share it over multiple servers, and all of that happens in the background, but we don't care about that today. So I will quickly insert our 3 documents we had here. And then I can simply search them. So I simply say, okay, I want to search my index. And in that index, I actually want to match everything. So what I could search over all the indexes, I could just search within that index, or I could even limit it down to, what was my type again? Was it quotes? Now I would only search within that type. But since I only have one type, I don't really care about it. I just say, okay, I'm searching within the index Star Wars. Since I have some other indices and I don't want that data to collide, I'm just saying, okay, I want to search that index Star Wars. And I want to match everything in there. And I run that, and phew, luckily it finds 3 documents, the ones we have inserted, and you can see them, okay, Obi-Wan never told you, these are not the droids, so no, I'm your father. So all 3 of them are here, and that's good. Now, one thing that might be confusing is I'm using a post here to search. Any ideas why? Sorry, what was that? Yeah, kind of compatibility, yes. So I could totally use a get here as well. And it works and it's the same. But what is the problem with the get here? Exactly. The standard does not define that there is a body, And there are some tools, like our tools won't do that, but there are some tools, especially if you have like these browser plugins which can do REST calls for you, they sometimes throw away the body of a get. Like some tools just send it along and others throw it away. The problem is if you throw away the body, your query will not do anything meaningful. And you will be wondering what is going wrong. So get is kind of the right verb to actually just read data, but it might cause problems sometimes. And depending on who is using the system or who is doing the talk, some prefer to have a get and others prefer to have a post. So I normally stick to the post, but it does not really matter. One is kind of not standard compliant and one is kind of the wrong verb to use in REST. So pick whatever makes sense for you, but yeah. I'm just sticking to get now. In that example and using post in the next one. So if I actually want to search something, I just say, okay, I want to search. And I actually want to match my in quote. I want to find everything that contains droid. How many results do we expect? 1. Exactly. These are not the droids you're looking for. And you can see stemming and stop words and everything worked. Like droids, I searched for droid and droids was found. What happens if I search for the plural? Any guesses? Will I find it or not? Yes, it is the same. Because the search term runs through the same analyzing pipeline that I do for inserting data. That is also the reason why once you have inserted data, you cannot just change the analyzing afterwards. Because you would need to re-index all your data with the new settings and configuration. Otherwise, it will just break. Okay, so now I want to search for dad. How many documents will I find for dad? 2. Why? Exactly, because we have synonyms defined. So we find 2 results, and no, I am your father, and Obi-Wan never told you what happened to your father. So synonyms are at work here. That is working nicely. Actually, some step I'm always skipping that. That is actually what is being stored in Lucene. So after storing your data, the list of extracted words is on the left-hand side, so those will be in alphabetical order. And then they will just say, each document I have, do I have the word in there, like how many times? And in the square bracket, I have added the position. So if you search for a phrase, it can actually then say, okay, these words are right next to each other, so they were a phrase. So this is basically what Lucene stores in the background as the index. It just extracts all the words you had or that remained after running through our pipeline. It knows where they were and how many times they appeared in a specific document and in the entire document body as well. So that is actually what storing looks like. One other nice feature is I can have fuzziness. So if I don't know how to actually spell Obi-Wan, and I spell it like with a V instead of a W, it will still find something. So if I search here, it will still find Obi-Wan. The score, we'll look into the score, how this is calculated a bit later. But this is, of course, worse than if I searched for Van correctly, then the score should be higher. And you can see, okay, one is 028 and the other one was 0118. So how does fuzziness actually work? Fuzziness is just the Levenstein distance. Levenstein distance is, if you have a Levenstein distance of 1, you can have 1 letter too much, 1 letter too little, and one letter different. If you have a Levenstein distance of 2, any of these 3 elements, there could be 2 changes. So 2 letters different or any combination of missing or too many. What auto does is, based on the string you have, like its length, it will pick a meaningful value. So for this query string I have here, the fuzziness factor will be 1. If the string is shorter, there will be by default a fuzziness of 0, and if it's more than 5 characters, it will have a fuzziness of 2 by default. But you can always select the auto fuzziness and will automatically pick that, or you can just set the number of differences very explicitly. So let's simply, we've done most of that. Come on, load. For fuzziness, you could of course do it like this in a relational database. But you can see that this is probably not much fun if you get longer strings. And it will also, again, because we have the wildcard at the beginning, doesn't use the index, so this will become very slow at some point. What Elasticsearch does with the wildcards or the fuzziness is, it will just brute force all the possible approaches. So that's also working quite nicely then. Okay, now let's shortly look at the scoring, like how do I actually get this quality attribute? So what is at work here is called TF-IDF, term frequency inverse document frequency. And what I'm saying now is just for a single term. So only as long as you're using a single term. If you have multiple terms, there will be something else at play. You will see in a bit. Actually, we changed the defaults in the current version, but it's still pretty much the same. You will see the curves are slightly different. So, term frequency. It's the square root of the frequency of a term. So if you search one term and the term appears multiple times in a document, that document is probably more relevant than if the term was only appearing once. So if I search for father, and one document contains father once, and another document contains father 3 times, the document with 3 times is more relevant than the father where father appears just once. That is the term frequency. And looks like this. So TF-IDF was growing stronger over time, whereas BM25 stays pretty the same. So the number of times my term appears, the more relevant it will be. So if you have a relevancy of 1, the square root of 1 is 1, and then it will just grow, and you can see, okay, if the term appears 5 times, it is way more relevant than if it was appearing just 1 time. That is term frequency. Then we have the inverse document frequency, which looks a bit more complicated, but it just says, okay, I have a term that appears that many times over my entire document body. Very rare terms are generally more relevant. So if you have a term that only appears once or twice over your entire document body, that is a very relevant term. Whereas if you have one term that appears hundreds of times over your entire document body, that is probably less relevant. And again, the curve looks something like this. So if the term appears just 1 time or 20 times or whatever, it has a very high relevancy. Whereas the more often the term appears, the less relevant it gets. So for example, if it appears 1,000 times, in BM25 it gets a relevancy of pretty much 0 anymore. Whereas in TF-IDF it still has some relevancy. But the general idea is like, very infrequent terms are very relevant and show like, okay, this is something special, you probably want to find this. And the next one is the field length norm. There's kind of the third big thing playing into that, which is pretty natural. If you have a very short field, if your search term appears there, it is probably pretty relevant. Whereas if you have a very, very long field, if your search term appears in there, okay, it's just many, many words, so it's not that relevant. So it's 1 divided by the square root of number of terms. You could explicitly fix that and say, okay, the subject is more relevant than the body of, I don't know, if you're researching emails, for example. But thanks to the field length norm, by default, the subject is very short. So if your search term appears there, it will have a higher relevancy than if it's just in the body of the email. So this will happen automatically in the background. And then you put it all together. You can explicitly boost specific fields. We'll look at that a little later. So you have TF, IDF, boost, the query norm. Those are the 3 main factors that actually contribute to what the score is of a term. And you can actually show that if you search for father, for example, and you add explain, it will tell you which are the contributing factors, how did I actually get to my result here. So it will tell you, okay, the overall score is 0, 4, 1, 9, whatever. And then we have IDF contributed that part, TF norm contributed that part, etc. So you can actually, if you're confused, like why is this document rated higher than another one, with explain you can actually see how is it calculated in the background and what is happening. You can of course do it by hand as well, but yeah, this is getting a bit complicated and I left my calculator at home, so we're not doing that today. So, 2 examples. I'm searching for father. These were the stemmed and stop-worded stuff that remains. Why is the first one more relevant than the second one? Exactly. So the term frequency is the same. Both have father once, so that is the same. IDF, inverse document frequency, father appears 2 times over my entire text body. That is also the same for both documents. The only difference is the first one is shorter than the second one, so this is a bit more relevant. And that's basically all there is. So what happens if I have more than one term I want to search? And especially what happens if I have a lot of terms and some documents might only contain some of these terms and others might contain some other terms, like which, of course, the document containing all the terms I'm searching for is the best match. But how do you rank other matches? Like, what is the difference if you search for 3 terms and one document contains 2 and another one contains 2 others? Which one is the more relevant one? Vector space sounds very fancy. So what you basically do is you score each term individually, then you draw it down in a vector, and then you calculate the angle to the perfect match, which is hard to explain, but easier to show. So since it's like each term adds 1 dimension, we'll just do a 2-dimensional thing because I can draw that very easily. So I'm searching for your and father. And my assumption is that your appears lots of times in the entire Star Wars movie. So this is probably not very relevant. Whereas father doesn't appear that often and is pretty relevant for the entire movie, but also over my data set then. So I assume that father is way more relevant than your. So if I draw that out, your, I give it a made up relevancy of 1, and father a relevancy of 5. And the perfect match would be this vector here. So your father, that is the perfect match. Now, which one is more relevant? A document just containing your or a document just containing father? And how we calculate that is we draw or vectorize the perfect match and then calculate the angle of documents containing just one of them. And the shorter the angle is, the more relevant it is. So father is way more relevant than documents just containing your. And if you have 3 terms, you will have 3 dimensions and more dimensions. But for easier thinking, let's just stick to 2. And this is the general approach of vector space model. Okay, some more features, other stuff we can do. So we've done that. Yeah. So if we search, in the beginning I said that databases are very much black and white. Full-text search or Elasticsearch can also do black and white searches. So I'm defining a Boolean query. You will only start loving SQL once you have written JSON queries. You can see the nesting can get kind of daunting, especially if you don't have autocompletion or syntax highlighting. So I define a query. It is of the type Boolean, and first I define it has a must. So it must contain the term father in the field quote. Only give me documents that contain that. And then I define it should also contain your and OB. But this is not a hard constraint. This is like just the more shoulds you have, the better your relevancy will be. So what is the output of that one? Two documents, yes. OB1 never told you what happened to your father, so we have OB your and father, and the other one, no, I am your father, your and father, no OB. And you can also see in the relevancy, like this is a bit more relevant than the other one. In this example, so the Boolean attributes I can use are must for hard constraint, should, must not to exclude, and filter. filter does the same as must, but does not contribute to the score. So if we look at an example of that, here, the only change I have done in that example is that here instead of must, I have filter. Watch these scores, they were 9, 6, and 7, 3. When I run that, they change. It was 9 something before, and now it's just 5, because father doesn't contribute now. Because I've just said, okay, I don't care about father, it should not impact my score. I'm just like filtering as a hard constraint. Like this is pretty much what a database does. It's just like a where clause, like this must be this, and only don't calculate the score. So the score is only based on the your and obi, and that is also the reason why it pretty much makes sense that this is nearly twice as relevant as the other one now, because this contains both terms and the other one just one. What you can also do is, which doesn't make too much sense, so this is the same example with must, but you can say the number of should elements you want to have is a specific number as well. So this is also like a must, but assume you had 3 terms and you said at least 2 of these should match. Yes, I know you can do that in a relational database as well, but it will be something like you will have an or and you have parentheses with this, this, and this, or you need to enumerate all possible combinations to do that. Whereas here I can just say my shoulds, these 2 should match. Okay, next time I will probably expand my example to have 3 terms to make more sense. But you can see it was otherwise the same query, and now I'm just getting 1 result because only this contains all my minimum should constraints. What you can also do is, I'm having the terms your and obi, and in this example I want to say obi is way, way more relevant. So I'm just boosting that by a factor of 3. So by default, the boosting factor is 1. So if I run your and obi, this is as if, this is pretty much the previous query we had, 0.9 and 0.7. So if I now say obi is way more relevant, or we can actually, let's boost yours, or your to change the order. So I can say boost 2, for example. Wait, I haven't run it yet. And now if I run it, oh sorry, your is contained in both, so that doesn't, no, that was a stupid example then. Let's run that. Okay, now we have 9 and 0.7, and if I run that with a boosting factor of 2, you can see, okay, this gets the value, the score just gets boosted way more now. And you can also say, you can do the opposite, so everything below 1 will boost it down. And you can see, okay, it's getting closer, maybe if I want to get that below. Yeah, since it has still more terms, you cannot get it below it because the other one doesn't contain that. It's just adding a bit on top of it, so you cannot get it above the other one. Yeah, but this here is, like, it will get down to a very similar. Yeah. Yeah, the second one is, now we've kind of crossed the boundary where the shortness kind of beats that having the second term. But it needs to have a very small boost factor to actually get there. So this is like lots of playing around how to actually get kind of the results you're looking for and you want to have. So we've done that, we've seen Boolean queries, we've done the boosting. Other stuff you can do. You can add suggestions. So you can, for example, search for something, and if nothing is returned by that search, it can suggest to you similar stuff. I'm skipping the example now because we would need to rework the mapping again, and this is getting more into the Elasticsearch details, and yeah. We don't want to go there. What you have, for example, if you search for fath and you don't find anything, and then you can just say suggest something that is similar to fath, and that will then find something. But again, you will need to have that changed in your mapping, that actually the information is extracted so you can have these partial matches there. And the other thing that can be very useful is Ngrams. For example, in German, when you have two nouns which are next to each other, you normally just combine them into one long noun. And that is pretty bad for full-text search, because if you just search for one part, it doesn't know what, Elasticsearch doesn't have a dictionary, so it doesn't know which is a word or which is two words. So for example, let's use an English example. If you have blueberry and you just search for blue, you will never find that in blueberry, because it's just blueberry as an entire thing, and blue just doesn't have enough matches. So if you want to be able to search for stuff like that, you can do Ngrams. For example, trigrams are pretty popular. Trigrams are just take a word and split them up into groups of 3 letters. So all possible 3-letter combinations, as you see in father. And then for your search term, split it up in those groups of 3 as well, and then find which other word in my document body has the most matches on groups of 3. And so you can find any partial matches. Or edgegrams are just taking from a string you have indexed every single word and taking from the start. By default, it has 1 and 2 letters, but you can say you can go up to 5. So it would have the first letter, the first 2, the first 3, the first 4. And then if you start typing, you would only start find stuff where you actually know how it starts, but not like find something in the middle. So you can then fine-tune whatever your users are expecting. If it's like on Google where you have the suggest feature, or you have like a mistyping, or you have fuzziness, you can just fine-tune whatever in your scenario makes sense, and then try to provide the right things. But it's all supported. So, to conclude, indexing just removes formatting, then you tokenize it, just breaks stuff into the different words. You can lowercase it, which normally makes sense. You remove the stop words, you stem everything down to the word root, and then you optionally can do your synonym matching. But you will need to provide these synonyms manually. There is no full dictionary or something that is generally applicable. You will need to provide your own. Scoring, we said the term frequency, the more often your search term appears in a document, the more relevant the term is. Inverse document frequency, less common terms are generally more relevant because, well, they are not that common, so they have more stringent meaning. And field length norm, shorter fields, if your search term appears in shorter fields, that has more value there. And yeah, once we were in a multi-dimensional space or multi-term space, we had the vector space model, which is easy to draw out in 2-dimensional space. Just keep that in mind, and that's pretty much how it will work for all the other dimensions. Yeah, if you want to try that out, we have our own cloud offering. It has a free trial, I think 14 days, so you can just click something together and play around with it there. So that's kind of the easiest way just to experiment and get started. And yeah, if you like it, you can keep your account. If you don't like it, just delete your account after some time, and that's it. Thank you. Other than questions, I have some stickers up front here. Oh, and I think we should take selfies with you. So everybody smile, please. Yes. Perfect. I think we managed to finish in time. Yeah, we have 5 more minutes.
Yeah, 5
Early
more
lunch
minutes,
or questions?
Hello, I have a question. Can you please explain the reason why Elastic doesn't support negation in text analyzing? For example, no or not. Because if you consider 2 different phrases, droids you are looking for and droids you are not looking for, they have absolutely opposite meaning from user perspective. And probably if I look these droids and not these droids, I would expect to get different results.
Yeah, the problem is full-text search does not do natural language processing. So it does not know the meaning. That is just different problem set. So what full-text search normally is, it's just you throw some words at it. It doesn't know if it's positive or negative. It just finds something that is similar. It does not know about good or bad stuff. That is just not what full-text search does. And I don't think any real system really, I mean, yeah, you have natural language processing, but that is normally very slow and also error prone. So for most use cases, full text search is what people are still using and kind of giving you the best results.
Okay, and as a result, you are not going to support this feature, am I correct?
Natural language processing. Well, of course, we're looking at academic papers, we have people playing around with different stuff, but no, at the moment, also Lucene does not do natural language processing, no. This is different problem area set. The only time I have used any natural language processing, I think, was at university. And just for one sentence, it was pretty slow. I mean, it was years ago. Yeah, so if it's feasible and it's easy to support, yes, we will do that. But no, not at the moment. It's just not in the scope.
Thank you for your talk. And my question is, how exactly index is used when fuzzy search is active? I mean, there is no VAN in index, only WAN, and how it works?
Sorry, for which term?
You used fuzzy search for VAN.
Oh, yeah.
But there is no VAN in index, so what
right.
should we do?
But there are all the possible combinations. It will just generate all the possible combinations and look like, do I have that word in the index?
Oh, but
if you have a fuzziness of 1, like you can just say, okay, one letter too much, one letter too little, or one letter different. And you just have lots of combinations, but you can just brute force that over. Because you have extracted all the words in the index, it is very easy to find that.
Okay, thank you.
And you can, for more advanced stuff with the Ngrams and Hgrams, there you will need to explicitly extract that. But of course, this is a trade-off, like if you extract it, it's more work to extract and more work to store, but then easier to find. If you have just the fuzziness, this is just query time overhead. But it does not add overhead for indexing. It's just storing the actual words and then just with brute forcing, like, okay, do you have this? No. Do you have this? No. Do you have this? No. And, oh, you have this.
Okay, thank you.
Hey, thank you for your talk. And my question is, can we change the scoring in any other ways? For example, it's a common case when we want to prioritize more recent documents to have a higher score and to be more relevant. Is it possible out of the box or requires some work, some additional work?
I'm just thinking about recent. I don't know from the top of my head. I assume you could probably do that manually, but I'm not sure how well that is supported, like out of the box. If you have like, you mean like it's decaying like over time, like radioactive decay, and the older it gets, the less relevant it is. Yeah, I will need to look that up. That's an interesting question. I don't know from the top of my head.
But is it possible to intervene the process of scoring to add such custom?
I have
stuff?
met someone. They used TF, but they got rid of IDF. You can disable that somewhere deep down. So it is only. I think it's a cluster-wide setting and not an index-wide setting, but you can disable, for example, in TF-IDF, you can disable parts. Not sure that really makes sense for many use cases, but yes, there are some parameters you can actually fine-tune.
Okay, thanks.
And what many people do when they're kind of not satisfied with the results is that they will do multiple approaches. So they will first they store the text as is, then they store it analyzed in the right language, then they store Ngrams or Hgrams, and they will search over all of that and just take the best results. So in academia, you always try to find the most clever approach, but in reality, generally the brute force approach, just add more hardware and just try multiple things and take the best result. That is what is yielding the best results, often. Yes?
Philipp, thank you for the presentation. Can I ask you, how do you support multi-language synonyms? So for instance, if I have 2 indexes, one on English and on Belarusian, and I'm searching for the father, and I would like also to find documents that have batka.
Well, you define a mapping, and if you use either a different index, you just define it in that mapping there, or if you use different fields, you also provide the different synonyms on that field. We defined it on fields. Like if we look at that example, if I go up here, where was my... Here I defined my synonym filter, then I put that into my analyzer, and my analyzer is just on that specific field. And then you would have my English analyzer, my Russian analyzer, my whatever analyzer. And you would just need to provide the different synonyms, add them to the right analyzer, and then apply the right analyzer to the specific field. But you need to tell Elasticsearch anyway which language that field is. Like Elasticsearch does not auto-detect your language. You will need to provide that and store it in the right field. There is no auto-detection of the language. We have Logstash, which can parse data, that can do language detection, but Elasticsearch itself does not guess the language. You will need to tell, like, I'm storing data in that language, and I'm then searching that with the right language.
Well, okay, that's not quite what I meant. So, for instance, if I have, for instance, in Canada, or in Switzerland, you have multiple national languages, and some documents can be in French, or some documents can be in for instance, in English. And I would like to find a document that have like divorce, for instance. I would like to have all documents for divorce, and I don't care about the language, so I'm also interested in French documents.
Okay. So it is still available. It will change in the future. We have, it's called an _all field, which is enabled by default. So you do not need to specify in which field something is. All the fields will be combined in that all, and you can just search over that all. So you can have the different fields for different languages, but they will everything will for each document be thrown into _all, and you can search over that. And then you don't care about the specific field, like is it the English field or is it the French field or whatever. You can just search overall, _all, and then it will find everything from every single field in that index.
Thanks.
Okay, we have no time. Thanks, Philipp.
Thank you.